Using local Bouguer gravity anomaly data, WSGG is able to reconstruct a three-dimensional representation of subsurface density bodies. Through a rigorous evaluation process, we are confident that the reconstructed density body closely approximates the true physical source responsible for the observed gravity anomaly field. In this video, we present key application results for an unconformity-related ore deposit. By providing clear three-dimensional images of the subsurface, these results can significantly assist geologists in identifying potential mineralization zones and determining optimal locations for exploration drilling. The cross-section shown here illustrates an unconformity-related deposit and the conceptual spatial arrangement of 6 major geologic units. From bottom to top, these units include basement rocks, graphitic metabolite or fault zones within the basement, altered basement metasediments, the ore body, altered sandstone, and overlying sandstone cover. For a detailed three-dimensional representation of this deposit, please refer to the separate video available on the WSGG channel titled Ore Deposit Model ABU. In exploration geophysics, we use remaining density, abbreviated as RODE, to characterize and distinguish between geologic units. The term remaining refers to gravity data after Bouguer correction, considered at either regional or property scale. In this study, we focus on remaining density contrasts between geologic units at property scale. For practical exploration applications, it is essential to impose as few preconditions as possible during the reconstruction process. Accordingly, any of these geologic units may or may not be present in the subsurface, and their geometries are not assumed in advance. Instead, they are determined directly by the gravity anomaly data. This table summarizes the 6 major geologic units and their corresponding remaining density characteristics for the unconformity-related ore deposit. It is not necessary to know the exact remaining density values of all geologic units prior to model construction. However, research papers and published studies often provide valuable guidance for qualitatively, and in some cases quantitatively, distinguishing their density characteristics. Such information forms an important foundation for identifying geologic units and constructing a subsurface ore deposit model. In this example, we assume that the ore body exhibits relatively high remaining density. The sandstone, altered sandstone zone, and graphitic metabolite or fault zones within the basement are assumed to have low remaining density, with the altered sandstone slightly denser than the unaltered sandstone. The basement metasediments and altered metasediments are assigned intermediate remaining density values. These assumptions represent deliberately loose constraints in the reconstruction and interpretation process and are applicable to most deposit types. This map displays the local Bouguer gravity anomaly used as the input for the reconstruction. Warm colors indicate Bouguer highs, while cool colors represent Bouguer lows. The anomaly is isolated and elongated in shape. Its long axis, striking approximately N31 degrees west, extends about 4,360 meters, while the short axis, striking N59 degrees east, measures approximately 2,215 meters. Such an anomaly may represent a localized Bouguer feature within a property, or a feature separated from a broader gravity field through potential field processing techniques. Based solely on visual inspection of the anomaly, it is not possible for either geophysicists or geologists to establish a clear relationship between the observed gravity response and the geologic units described earlier. At this stage, geophysicists naturally ask, and are often asked by geologists, several fundamental questions. Where is the source of the gravity field located in the subsurface, and what are its depth, size, and geometry? Is the source internally homogeneous, or does it exhibit heterogeneity? If it is heterogeneous, how many remaining density components does it contain, and how are these components distributed underground? Addressing these questions constitutes the primary objectives of geophysical interpretation. This three-dimensional view presents the reconstructed remaining density body derived from the input Bouguer gravity anomaly. The color scale represents the reconstructed remaining density. To distinguish these values from true physical density contrasts, we refer to them as inverted remaining density, abbreviated as IRD. Overall, the reconstructed density body is expressed as a large set of points that naturally cluster in three-dimensional space. Each point is defined by its spatial coordinates and associated IRD value. This self-organized spatial pattern is visually clear and highly encouraging, as it provides both geophysicists and geologists with improved insight into subsurface rock distributions. The critical question, however, is whether this reconstructed body represents the true subsurface structure to an acceptable degree. Addressing this question requires a formal evaluation process. The three maps shown here, from left to right, display the input Bouguer gravity anomaly, the expected anomaly calculated from the reconstructed model, and the resulting anomaly misfit. All three maps share the same color scale for direct comparison. The misfit range is indicated on the color bar. A low misfit magnitude combined with a narrow value range indicates a high degree of agreement between the observed gravity data and the calculated response. This close correspondence demonstrates that the reconstructed body provides a reliable representation of the gravity field source responsible for the observed anomaly. It should be noted that the misfit does not appear uniformly smooth at a low level, as suggested by the third map. This visual effect results from using the same color scale to display both the Bouguer anomalies and the misfit. When a smaller, more appropriate color scale is applied, the misfit reveals a more detailed and irregular pattern across the reconstructed remaining density source. Such misfit can arise from several factors, including input data error and uncertainty, errors introduced during data processing, and numerical or computational limitations. In this case, however, the overall misfit remains at a very low level. This level of agreement allows us to proceed with confidence to the key interpretive question: what does this reconstructed remaining density body represent geologically? The reconstructed remaining density body exhibits spindle-like geometry. Its long axis is approximately 3,500 meters in length, striking N 31 degrees west, while the short axis measures about 1,275 meters, striking N 59 degrees east. Vertically, the body extends from an elevation of approximately 25 meters at the base to about 1,125 meters at the top, giving a total vertical extent of roughly 1,100 meters. The total volume of the reconstructed body has been calculated to be approximately 1.796 billion cubic meters. To examine the internal structure of the reconstructed body in greater detail, a representative slice, labeled A, has been extracted from the volume along its long axis. This map shows the plan view of the reconstructed body, highlighted in gray, together with the location of the AA slice, indicated by the red line. This three-dimensional view illustrates the position of the selected AA slice within the subsurface volume. It provides a clearer representation of the reconstructed body, showing how rock densities are distributed along AA in the subsurface. The reconstructed body clearly exhibits internal heterogeneity. This is the inverted remaining density, or IRD, cross-section A, derived from the extracted slice. The horizontal axis represents distance from endpoint A, while the vertical axis corresponds to elevation. Warm colors indicate high IRD values, whereas cool colors represent low IRD values, with mid-range IRD values shown in yellow. From this cross-section, we can clearly observe the internal structure of the reconstructed body, allowing for straightforward geophysical interpretation. Based on the density characteristics of the geologic units, we first identify the following features on the cross-section. A. The relatively high IRD zones, shown in orange and red, correspond to the basement rocks. B. The lowest IRD zones, colored in cyan or navy blue, correspond to the cover rocks, namely sandstone. These interpretations are fully consistent with fundamental geological knowledge. Second, we consider the location of the unconformity. From both geological and morphological perspectives, the unconformity should occur within the transition zone between the cover rocks and the basement. On the cross-section, most of the mid-range IRD values are concentrated near an interface separating these two units. Accordingly, we infer that the unconformity is located within the yellow-colored layer. It is also noteworthy that an upward rising feature appears in the central portion of the cross-section. While this is atypical for a regionally smooth and relatively flat unconformity, at the property scale it may reflect localized structural features affecting both the cover rocks and the basement. For this reason, the inferred unconformity, shown as a dark dashed line, is intentionally left discontinuous in the central area. Third, the most prominent feature on the cross-section is a bulge, located in the central portion, labeled by markers 1 through 5. This bulge originates at the top of the inferred basement, protrudes through the inferred unconformity, and extends upward into the overlying sandstone. We interpret the area enclosed by this feature as the main ore deposition zone, simplified as MODZ. From both geophysical and morphological perspectives, the bulge is interpreted as a composite structure consisting, from bottom to top, of altered basement rocks, the ore body, specifically the zone marked as 4, and overlying altered sandstone. A natural question arises. Could this bulge represent a different, previously unrecognized geological structure? The answer is unequivocally yes, it is possible. This question and its answer highlight a fundamental principle of geophysics geology integration. Geophysical evidence cannot be directly equated with geological evidence. Geologists must evaluate geophysical interpretations carefully, in conjunction with their geological knowledge and supporting information. Finally, by closely examining the lower left portion of the inferred MODZ, we identify IRD depressed zones within the basement, labeled as 6 and 7 on the cross-section. This is a significant feature. The two sides of this depression are asymmetrical. The right side is noticeably steeper than the left. Both theoretical studies and exploration practice indicate that step-like density variations can be indicative of faulting. Accordingly, we interpret this feature as a fault or a graphitic metabolite zone. The dip angle is qualitatively estimated by integrating all surrounding IRD features observed on the cross-section. Identification of a fault or graphitic metabolite zone is particularly important, as such structures often represent fluid conduits or paths active during mineral deposition. By deconstructing the model based on inverted remaining density values, we can achieve a comprehensive understanding of all interpreted components, including the cover sandstone layer, the unconformity, the main ore deposition zone, the basement rocks, and the fault or graphitic metabolite zone within the basement. This three-dimensional view illustrates the inferred unconformity in subsurface space. Overall, the unconformity is smooth and relatively flat, with a gentle dip toward the southwest. Its elevation is slightly higher in the northeast than in the southwest. On closer examination, a localized uplift can be observed along the short axis of the spindle-shaped body. This feature corresponds to the inferred ore zone, consistent with the area previously labeled as 4 on the cross-section. Based on this observation, we infer that the ore deposition zone strikes northeast, approximately parallel to the short axis of the reconstructed body. This interpretation can be further tested and validated by generating and analyzing a series of slices parallel to cross-section AA. This three-dimensional view displays the cover rocks above the unconformity, shown in green, cyan, and navy blue. These colors represent the mid and low IRD components in geophysical interpretation. Upon examining the upper portion of the cover rocks, a prominent cavity, or large void, can be observed. This feature provides important insight into the internal structure and spatial variability of the overlying sandstone unit. This three-dimensional view displays the rocks immediately above the inferred unconformity, shown in green and cyan. These colors represent the mid and low IRD components of the reconstructed body in the geophysical interpretation. The most prominent feature in this view is the upper portion of the bulge, which has been interpreted as the main ore deposition zone, or MODZ. This upper part of the bulge includes both the ore unit and the altered sandstone unit. The three-dimensional visualization reveals the full subsurface geometry of the bulge. By generating and interpreting a series of slices parallel to cross-section A, it is possible to estimate its volume. This three-dimensional view illustrates the basement materials beneath the inferred unconformity. These units are displayed in orange, red, and magenta, representing the mid to high IRD components of the reconstructed body in our geophysical interpretation. Since mineral deposition likely occurred on both sides of the unconformity, we now examine the basement materials immediately beneath the inferred unconformity. This view reveals the lower portion of the bulge, showing its geometry and the depth to which it extends downward into the basement. At the base of the bulge, the basement rock displays a narrow, saddle-shaped structure, roughly aligned with the short axis of the reconstructed body. This local geometry corresponds to the ore zone identified in the cross-section interpretation. By generating and interpreting a series of slices perpendicular to the short axis, it becomes possible to estimate the three-dimensional volume of the ore zone in space. To summarize, we have achieved the following geophysical objectives: reconstructed a heterogeneous density body that represents the gravity field source responsible for the observed Bouguer anomaly. Identified and inferred the components of the density body corresponding to major geologic units of an unconformity-related ore deposit, including A. Cover rocks, sandstone; B. The unconformity; C. Basement rocks, metasediments; D. Altered sandstone and ore zone; E. Altered basement and ore zone; F. Fault or graphitic metapolite zone. Determined the locations, depths, sizes, and geometries of these components. Conducted geophysical and morphological analysis of the main ore deposition zone.